Welcome everyone. Today we'll begin our journey by exploring the history and foundational concept of interpretability in deep learning. A bit of theory to soak up while the sun shines bright outside here in Toronto. But I promise to keep it short and clear.
We'll begin with a historical overview and context, recognizing the key milestone and many contributions that brought us to the present state in deep learning. This session aims to provide foundational concepts essential for understanding the rest of the course. So, before we dive into the details, let's recap the course plan that we have outlined in our introductory session. We will start with the concept introduction. For the next 30 to 45 minutes, we will cover crucial backgrounds, concepts, and foundational theories that shape modern deep learning and form the basis for the need of interpretability in AI. This will also provide context for advanced topic we'll discuss later in the 5 modules, that is explainable approaches, model agnostic techniques, neural network and explainability, and lastly ethics and emerging trends in AI. So, from the inception of the first AI concept in 1943 to the revolutionary breakthrough we witness today, this segment will highlight significant milestones and key developments that have shaped the AI landscape. Given my experience, understanding the history is crucial to appreciate the future of AI. Next, we shall very quickly step into the challenges posed by the black box AI model. This topic will provide a solid foundation for understanding the core challenges and considerations in making deep learning model interpretable. Here is a comprehensive timeline of significant events in AI, which you can also find in our book Interpretability in Deep Learning, published in 2023. To make it more digestible, I have broken it down into smaller segments. The journey begins with the early fascination with human brains, leading to the first model of a neuron in 1943. Though we have learned that modeling the brain's processing is far more complex than initially thought, this was a critical starting point for what we now call deep learning. A key question remains: how can a child learn from a language with so little data? This curiosity continues to drive research in present day. Another philosophical question that fascinated researchers was whether a machine could think like a human. This led to the famous Turing test in 1950, which asked if a machine response could be indistinguishable from a human's in a written interaction. In the 1950s, AI began to establish itself as a discipline. One of the early milestones was the development of a checker playing program by Arthur Samuel in 1952, which showcased the potential for machine to learn and adapt. Next, people were soon introduced to symbolic AI, which aimed to bring logical reasoning into machines. This was further advanced by the 1956 Dartmouth Conference, organized by John McCarthy, which brought together leading researchers to discuss the future of AI. This conference marked a pivotal moment in AI history. In the late 50s, we saw the introduction of perceptron, a foundational model for neural network, and the development of the Lisp programming language, crucial for AI algorithm. The General Problem Solver, also called GPS, created in 1957, was another significant milestone, demonstrating the ability to solve complex problems like the Tower of Hanoi. Moving into the 60s, we witnessed advancement in neural language processing, pattern matching, and the introduction of Bayesian methods for probabilistic reasoning. The development of ELIZA in 1964, an early chatbot simulating a psychotherapist, paved the way for intelligence support system and clinical decision support tools. The 60s also saw the emergence of expert systems and symbolic reasoning, with significant work in organic chemistry showcasing the practical application of AI. Despite these advances, funding for AI research experienced setbacks, such as the 1966 LPAC report, which criticized progress in NLP, leading to funding cuts. The 70s brought backpropagation and automatic differentiation, fundamental for training neural networks. Despite setbacks like funding cuts, AI research continued to progress, leading to innovations like the convolutional neural network (CNN) introduced by Fukushima in 1979. The 80s saw the popularization of backpropagation and the introduction of practical applications like handwritten character recognition by Jan LeCun, along with the rise of belief networks and Bayesian methods. The 90s marked significant milestone with support vector machine for classification and the introduction to large datasets like MNIST, essential for training complex models. The victory of IBM's Deep Blue over Kasparov in 1997 highlighted the potential of AI in game playing, and the development of long short-term memory, commonly known as LSTM models, expanded AI's capability in processing sequential data. As we entered the 2000s, modern deep learning emerged with the advancement like the Boltzmann machine, large image dataset, and the introduction of word embeddings. The introduction of generative adversarial network, commonly known as GANs, by Ian Goodfellow in 2014 revolutionized the field, allowing for the generation of realistic images and other data types. DeepMind AlphaGo's victory over world champions Lee Sedol in 2016 demonstrated the advanced strategic capabilities of AI, and the rise of transformer network opened new possibilities in NLP. As AI continued to advance, ethical considerations have become increasingly important. Issues like biases in datasets and the transparency of AI decision-making process are critical to address. The challenges of interpreting AI model, especially black box models, remains a significant concern. Understanding how decisions are made is crucial for trust and accountability. In conclusion, while AI made incredible strides, the need for interpretability and ethical considerations is paramount. We'll explore this topic in depth throughout the course, ensuring a comprehensive understanding of both the technical and the societal implications of AI. Since we humans are more of a visual learning creature, a visual history shall help cover this topic quickly while having your continued attention. Here is a comprehensive timeline of significant events in AI, which you can also find online. To make it more digestible, I have broken it down into smaller segments. Although we can't cover everything in detail due to time constraint, we'll touch upon the major stages briefly. In the 1940s, the question of whether machine could mimic human intelligence emerged. This philosophical inquiry led to the development of the Turing test in 1950s, designed to evaluate a machine's ability to exhibit intelligent behavior indistinguishable from human. The 1950s also saw the establishment of AI as a discipline. One of the early milestones we discussed was the development of a checker playing program by Arthur Samuel in 1952, which showcased the potential for machine to learn and adapt. Another significant development was the introduction of symbolic AI, which aimed to bring logical reasoning into machines. The famous 1956 Dartmouth Conference, organized by John McCarthy, marked a significant milestone, gathering pioneers like Minsky, Shannon, and McCarthy himself to brainstorm AI concepts. Their discussion laid the groundwork for the programming computers, including generalization and hypothesis formation, which are essentials to modern AI. Another significant development was the introduction of symbolic AI, which aimed to bring logical reasoning into machine. In the late 1950s, we saw the introduction of the perceptron, a foundational model for neural network. It demonstrated that a machine could learn from data by adjusting weights iteratively. Around the same time, the programming language Lisp was developed, which became essential for AI research in 1958. In the early 1960s, the general problem solver was developed, capable of solving simple problems like the Tower of Hanoi. However, as problems became more complex, the limitation of early AI became apparent due to combinatorial explosion. The development of probabilistic methods, such as the universal Bayesian inferences, also took place in 1960s. Solomonov's work on algorithmic probability was groundbreaking, predicting future sequences of symbols based on the past data. In 1964, Joseph created the ELIZA program, an early example of a conversational agent that simulated a psychotherapist. This paved the way for intelligence support system and clinical support staff. Natural language processing, or NLP, made significant strides during this period. The solving of algebra word problems by D. Bobrow in mid-1960s was a key achievement. Expert systems also emerged, aiming to encode human experts' knowledge into machine. The introduction of fuzzy logic by Chedha in 1960s added a new dimension to AI, allowing for reasoning with uncertain and imprecise information. This concept remains crucial in modern AI and deep learning models. The 60s also saw the emergence of symbolic reasoning, with significant work in organic chemistry showcasing the practical application of AI. This was demonstrated in the Dendral project, which used expert knowledge to infer molecular structure in organic chemistry. In the late 1960s, the robot Shaky was developed, considered the first general-purpose mobile robot. Shaky used a form of intelligent search known as A-star search, which was a significant step towards autonomous robotics. The era also saw advances in probabilistic reasoning and early NLP techniques. Despite these advances, funding of AI research experiences the second winter wave or the setbacks, such as the 1966 LPAC report, which criticized progress in NLPs, leading to reduced funding again. The 1970s also brought the development of computer-assisted diagnosis systems like Mycene, which provided medical diagnostic advices. Also, backpropagation and automatic differentiation, fundamental for training neural networks, were developed. Logical programming languages such as Prolog emerged in the 1972, facilitating the encoding of knowledge and inference rules. This was crucial for developing expert systems and other AI applications. Despite setbacks like the 1973 Lighthill report and funding cuts, which criticized the lack of progress in AI, research continued to progress. We all witnessed the impact of the first convolutional neural network introduced by Fukushima in 1979. The 80s saw the popularization of Bayesian network by Julia Pearl and backpropagation by Hinton, Rumhard, and Williams, a fundamental algorithm for training neural network. These advances laid the groundwork for modern deep learning. In the late 1980s, CNNs were used for practical applications such as handwriting recognition by Jan LeCun. The 90s introduced support vector machines for classification and emphasized the importance of large datasets like MNIST, essential for training complex models. The MNIST dataset, introduced in 1995, became a benchmark for evaluating machine learning models. In 1997, IBM's Deep Blue defeated chess champion Garry Kasparov, highlighted the potential of AI in strategic games. This was followed by the development of LSTM networks by Schmidt Huber and Hochreiter, expanded AI's capability in processing sequential data. Entering the 2000s, deep learning research accelerated. Significant milestone introduced the development of Boltzmann machine and large language datasets such as ImageNet, which fueled the success of models like AlexNet in 2012 challenge. The introduction of word embeddings by Miklov in 2013 and the introduction of generative adversarial network by Ian Goodfellow in 2014 revolutionized the field, allowing the generation of realistic images and other data types. In 2016, DeepMind's AlphaGo defeated Lee Sedol in the game of Go, highlighting the potential for reinforcement learning. This victory raised questions about the future of AI and its capability, and the rise of transformer network opened new possibilities for NLP. However, as AI continues to advance, ethical considerations have become increasingly important. Issues like biases in datasets and the transparency of AI decision-making process are critical to address, as biased dataset can lead to biased outcomes. This is a significant challenge, especially in critical applications like surveillance and law enforcement. MIT Media Lab did the empirical biases in gender shades in 2018, and many followed after. The deeper we dig, the more remnant of biases we will find in our technology. We cannot afford to look away this time because the stakes are simply too high. In gaming, AI continues to achieve new milestones, such as Alpha Star reaching Grandmaster level in DeepMind's StarCraft 2. This advancement illustrates the growing sophistication of AI. Today, the use of AI in manipulating elections and analyzing personal data led to broader societal debates about privacy, bias, and accountability. In May 2023, few notable AI leaders warned about risk of extinction in an open letter that caught a lot of our attention. In June, an artificial intelligence task force advisor to the UK Prime Minister has a stark warning that AI will threaten humans in 2 years. The challenge of interpreting AI models, especially black box model, remains a significant concern in 20s. Understanding how decisions are made is crucial for trust, and accountability is becoming the driving force for many big companies. In summary, while AI has made incredible strides, the need for interpretability and ethical considerations is paramount. We'll explore these topics in depth throughout the course, ensuring a comprehensive understanding of both technical and societal implications of AI. Looking at recent headlines, we see concerns about the potential threat posed by AI. This brings us to the concept of black box model, a model that hides the detail of how it works on the inside is called a black box model. This makes it hard to explain why a certain prediction was made. Deep learning models are often called black box models because it's hard to see what happens inside them and how they make decisions. There are AI systems whose decision-making processes are not transparent, raising questions about trust and accountability. As we move forward, it is essential to remember that AI's impact is not just technical but also deeply ethical. The ability to interpret and understand AI decision is crucial for building trust and ensuring accountability in applications ranging from healthcare to autonomous driving. So, not knowing how a model comes to a conclusion isn't a solution anymore. The use of such model for safety critical tasks is dangerous and subject to serious ethical concerns. And so, we are here to expand our understanding that if an AI system makes a mistake, who is liable? The machine, its developer, or the data providers? These are important questions we'll explore. For example, in autonomous driving, if an AI controlled car causes an accident, determining liability is complex. We need to ensure these systems are accountable and transparent. Alright folks, at the very end, the figure presented in the book Interpretability in Deep Learning is a take-home message on the characteristics of different popular methods competing for accuracy versus interpretability. From simpler linear models, rule-based learnings and decision trees to complex ensembles and deep learning systems. We'll delve deeper into this topic, including emerging techniques and ongoing research throughout this course. The three key trade-offs being completeness versus interpretability. We'll discuss the balance between having a complete comprehensive model and one that is interpretable. Often increasing interpretability might mean sacrificing some complexity or details in the model. Another important trade-off is between the efficacy of AI models and the privacy of the data they use. We'll examine how different approaches can affect this balance and the ethical considerations involved. Finally, we'll look at the trade-off between providing human understandable explanations and maintaining high accuracy in AI predictions. Striking the right balance is the key to ensuring AI systems are both effective and trustworthy. As we wrap up, remember that as AI continue to evolve, so must our methods for ensuring that these systems are fair, transparent. Thank you for your attention. I am confident that by the end of this course, we'll not only understand the technical aspects of AI, but its broader implication for society. Feel free to ask questions during the physical session in August or comment on the recorded video and participate actively. Your engagement is crucial for making this learning experience enriching and impactful. Thank you.